As engineers, our job is to not only maintain current products and systems, but to see if we can innovate or re-engineer a better design. A design that uses less memory, less energy, or maybe even less humans to make a simpler but better world. The purpose of our project is to create a self-sustaining flower pot, a device that takes the thought and time out of owning and caring for plants. This would allow the user to grow healthy houseplants with almost no effort or prior gardening knowledge.
My name is Zachary Avila. I'm a senior computer engineer, and for our project Plant Buddy, I took the lead in hardware development and firmware programming for our Arduino.
My name is Cole Constantino. I'm a senior computer engineer at Case Western, and I took the lead of the task or project manager throughout, as well as the lead developer in the iOS application.
My name is Arthur F., and I'm a senior computer science major at Case Western. And in this project, my role was the lead researcher and software tester. So in the first phase of the project, I mostly just researched the right hardware and software solutions to use for our device, and in the later phases I took over the software aspect and built tests for the Xcode application.
There are relatively similar products out there, but they are surprisingly limited. They are what's known as passive plant watering systems that essentially slowly drip or feed water at a constant rate until its holding tank is empty. One that demonstrates this process is on the right. It is a tank with a canal that sticks out of the bottom and directly into the soil. The canal is small enough to make the drip gradual and constant. This is a good way to let gravity do the work, but there are setbacks. On the left you can see an irrigation system, which is similar but uses valves to send water at intervals to the emitters and plants. A big problem with these systems is that different plants require different amounts of water. Some require daily, while some require weekly. This results in overwatering and underwatering, and essentially an unhealthy, shorter plant life. Our approach to this autonomous flower pot was to build a containment around it. In the bottom compartment is all of the hardware. This includes sensors to measure the moisture in the soil, a watering pump, Bluetooth microcontrollers, and a power supply. From an iOS app we had made, the user is able to select a plant from our database that they are using in the pot. The pump will grab water from the holding tank and distribute it into the soil. In the back end of the app, the plants have exact specifications, such as healthy moisture levels and exact timings of when to water the plant based on the sensor readings. When a plant is selected, the app sends a detailed signal to our system to run the given instructions, and voila, you have a plant that can take care of itself. A critical software tool we used in our design was the Arduino IDE. With that, we were able to configure our circuit hardware, moisture sensors, and microcontroller, and program them to do what we wanted. Another critical software tool we used was Apple's Xcode IDE. With that, we were able to design an iOS app to connect to our system and control the hardware specs. Unfortunately, due to the worldwide pandemic, our design was limited to just an external system. The system does have the complete functionality we wanted in design. However, after leaving campus, we were not able to 3D print a containment to structurally and aesthetically hold all the moving parts. The upside of this is using however large of a holding tank we want. With enough water, our system could keep a plant healthy and watered for months on end.
The hardware for our project Plant Buddy is comprised of 4 main components. The 5-volt power supply, which is used to power our project. The 5-volt water pump, which is used to pump water from our water reservoir into the plant itself. Our capacitive soil sensor, which was used to take moisture level readings of the soil, and it uses I2C data transfer to send that to the microcontroller. The microcontroller is the final component of our hardware. Initially, we were planning on using the Arduino Nano, and we were going to have a separate Bluetooth module so we can connect our hardware to the iOS app that we built. However, we found it easier to use the Adafruit Feather 32U4 microcontroller, which has built-in Bluetooth module, and it has a ton of free online libraries, which made it a lot easier for us to connect. This clip here shows me connecting our capacitive soil sensor to our breadboard. I'm hooking up the ground, the voltage in, and then I'm connecting the SDA and SCL inputs, which are needed for the I2C connection. Now you see me opening the serial output terminal for our Arduino and opening the app that we built to connect to it. Now I'm connected to the breadboard itself, and now I'm setting the plant to a fern. Here you can see me demoing the on and off switch, which turns on and off the pump whenever you need to if you want to give your plant a little bit of extra water. Now you can see me demonstrating our soil sensor capacitance changing when I'm touching it or not touching it. You can see when I'm touching it, it's at about 1,000, and when I'm not, it's at about 300. Here in this clip, you can see our final project actually being demoed. We have all our hardware set up right here on the right, and it's connected to my laptop so we can get the serial output readings, but it doesn't have to be. Here you can see me connecting our app to the actual hardware, and I'm setting the plant as a fern, which is going to go ahead and start it watering. The water was already somewhat damp, so it starts at about 450 to 500, and then as you can see here, here's our hardware setup. We have our water reservoir on the right, we have our pump in the middle, and then the plant on the left. The other end of the pump is going into the plant. You can see our Arduino and the rest of the hardware in front of it, and then we have our capacitance soil sensor in the soil itself. Here you can see the capacitance level slowly dropping, and once it reaches under 300, it's going to go ahead and shut off the water pump, since this means that our plant is thoroughly watered.
So we did come across some technical constraints, which were to be expected, but the only significant obstacle was establishing a connection between the pot and the software controlling its devices. Since Apple's software is closed source and lacks accessibility, we couldn't establish this connection the way we initially intended, using a third-party Bluetooth adapter. So this led us to eventually finding a microcontroller with a built-in Bluetooth system that we could connect to Apple's Xcode IDE directly.
Overall, our project was a success. We didn't get to 3D print an actual structure to hold all the moving parts and hardware, but in the end we did create a fully functioning system to take care of a plant indefinitely. Not only that, you can do this remotely via an iOS app.